Hello, welcome to another Minecraft clone tutorial series. Today I'm going to be showing you how to make a 3D camera in your Minecraft clone game. This is going to be a bit of a difficult tutorial compared to the other ones. I'm going to have to do a lot more writing code and explaining later in this one, but it shouldn't be too bad. I'm going to make sure to go into depth with everything and make sure I understand everything. I thought in this tutorial, first I would show a simple demo of this working. I realized that in the other tutorials, I wasn't showing the finished product or any sort of demo, and I don't think that's very fair to you guys, so you don't really know what's going on. So I thought I would go ahead and show a simple example of how this camera works. This is another clone that I made a little while ago. It's a bit further along than this tutorial, but don't worry, we will get here very shortly. So here it is. It's a very simple clone. It's just a one chunk render. And we have this camera here, and as you can see, this camera has a 3D movement. We can look around with the mouse. We also have where you can press space and it goes directly up, and shift and it goes directly down, and you can look up and look down, and it doesn't let you do any weird things where you can go past this distance. So all of these features we're going to be adding in this tutorial today, so let's get into it. So getting into this tutorial, back in our original code, we're going to have to add our first additional file that we're going to be adding to our game here. That is an actual C# file. So we're going to be exiting this game.cs for the first time. So here in the project, I'm going to right click and I'm going to do add new item, and then I'm going to do camera.cs. And here we have our new camera class. And so here I'm going to sort of write out all of the empty methods that we're going to need right away. So the first one is the constructor, and then we're going to need a public, and it's going to be a we're going to need a mat4, and it's going to be get view matrix. And here we're just going to ignore this for now, even though it has red. Don't worry, we will get to this. Then we want to do a public matrix4 get projection matrix. Okay, and I'm going to change this to a capital. And then there's a couple other ones we need to do. We need a simple update method that we can call every single frame. This is just going to be a public void update. And we can go ahead and put in the arguments for this already. So it's going to take in a keyboard state. This is for handling inputs. And then we're going to take in a mouse state, and this is for handling mouse inputs. And then it's going to take in a frame event args, if I can spell it right, frame event args e. And that's it for now. And now we need a couple more methods here. I'm going to do an input controller method. This is going to handle all of our inputs. So we're going to do public void input controller. And this is also going to take the exact same arguments as the update, Control C, Control V, and then just keep that as an empty method. And then here we can actually go ahead and just put a call to the input controller and send it all those arguments. And that is our update method done for now. So now we have just one more method that we need to do, and this is our update vectors method. So we're going to do a private void update vectors. And now with all of this, let's go ahead and start getting into it. So first I want to explain a couple of things. So this camera is going to be messing with the view and the projection matrix, because originally we were using the view and projection matrix, but we were simply we're just typing them here, and then we ran it, and we had no way to change them after we ran the code. And so here we want to be able to use this camera and update the position and rotation and all that stuff of our view every single frame. And so we're going to be messing with these two matrices. The model matrix is not affected, because remember, the model matrix is what's used to translate our object into world space. And we don't want to be actually moving our objects in world space. We want to simply be perceiving them in a different position. So the model matrix will stay the same. So now with this view and projection, now that we know that that's what we're going to be doing, let's go ahead and get into how to use this. So this is where it gets a little bit more linear algebra in depth, and I've linked a couple things in the description to help further explain this. It's a little bit beyond the scope of this video to teach linear algebra, but I will be showing you how to implement it properly. So we're going to need some constants here. So I'm going to make a section called constants, and I'm going to do a private float for a speed. I'm going to set this to 8f. And then I'm going to do a private float for the screen width, and same with the screen height. And then we need a sensitivity, private float sensitivity. And this is for this is used for our looking around. And I'm a person that likes a sensitive camera when I play games, so I'm setting mine really high to 180 degrees, or well, not degrees, but 180. But that's, you know, you can always just tweak it to your own liking. We need one variable for position, and this is going. So I'm just going to do position variables, and I'm going to do a public vector3 position, making it public because we will access it in other parts of the program. And then we need a couple things for calculating our matrices. So here we're going to create a couple things. Right now, even though we're in a 3D context, and you could probably assume that we're going to be using with the X, Y, and Z axes, there's no specific order and direction that each of these go. So we're pretty used to having Y going up, X going to like side to side, and Z going forward backwards. But according to this, since we're making our own sort of engine here, there's no reason for that to be true. For example, Blender uses Y going forward and backwards when you first start it up, and Z going up and down. That's just because they chose to have it that way. So here we're going to have to choose what our up is, and all that stuff. Well, what our up is, what our front is, what our right is. So with that being said, let's go ahead and make these variables. So for this, we're going to make 3 vector3s. The first vector3 is going to be our up, and this is going to be equal to the vector3.unitY. And so if you hover over unit Y, it'll say defines a unit length vector3 that points towards the Y axis. So we're just defining our up as Y, because I think it's a little easier to think of Y as up, just because that's how I think personally. But if you want to change it, you can. I recommend sticking with the way I'm doing it though, but I'm going to define vector3 front, and this is going to be as vector3.unitZ, and this is because I want forward and backwards to be this unit, or on the Z axis. And then I'm going to do right as vec3 right, and this is going to be as vector3.unitX. So now we have defined that our up is the Y, the going forward and backwards is Z, and then going right is on the x-axis. So with this, we can get some basic movement going. So the first thing I'm going to do is I'm going to actually do just get our projection matrix out of the way, because we can already do it pretty easily. So the projection matrix, all it's going to do is it's going to return a matrix 4, or a matrix 4 dot create perspective field of view, and this is going to be a math helper dot degrees to radians, and this takes in our field of view. And you can store this in a variable if you want. I never change mine, but if you want to, you can. I'm just going to make mine 45 degrees. And then we have the aspect ratio, and this is going to be our screen width and our screen height. And it's important that you have these stored as floats and not ints, because you don't want any sort of rounding here, or you're going to get distortion. So we want the screen width divided by the screen height. The next one is the depth near, which is the closest things that are rendered, and then the depth far. Remember last tutorial, we simply made them 0.1 and 100f. It doesn't matter if you change this, it'll just render at different distances. This is just what most tutorials do, so I'm going to stick with that. And with that, we already have that entire method complete. So now we can move on to the next couple of methods. First, let's go ahead and get this constructor working, so we have some values for these variables. So we're going to want to center a constructor, the screen width, the screen height, and then the position as a vector3. This is going to be the position of our camera. And then we're going to do screen width equals width, screen height equals height. I don't know why it doesn't have the same line. And then this dot position equals position. And now with that being done, we can now use this get view matrix. And this get view matrix, we will simply return a matrix 4 dot look at. And this is going to be position, and then position plus front, and then up. And if we go to the arguments of this look at, it is the eye, which is basically where we are, where the actual camera is, the target, which is our position pointing towards the front, which is what we defined as front, and then we have to define what up is. And so we defined up as y in the positive direction. So that is what up is here. And so now what we can actually do is we can use this as our simple static projection, or a static replacement of this view and projection here, even though we don't have any functionality yet, just to prove that it works. Let's go ahead and add it real quick. So let's go into our like fields here. I'm gonna make a new section, and I'm going to just call this camera, and I'm gonna do a camera, very original. In the on load here, I'm going to load in our camera at the very bottom, camera equals camera, and this is going to take in the screen width and the height, so I think it's the width, height, and then we need a position. And I'm just going to do a vector 3.0, which just sets it at the origin. And let's see. Oh, I'm coding too much in Python, need that new word. Anyways, now that we have that, we can simply use it here instead of doing this manually here. So instead we can do matrix for view equals camera dot get view matrix, and then here we can do matrix for projection equals camera dot get projection matrix. And now we can simply run this, and we don't see anything yet. It might be that we have the front facing the opposite direction. Let me check real quick. Yes, it was that. Okay, so I forgot that the moving forward should be the negative z, because remember, by default moving, like translations, moving away from the default origin is moving in the negative z direction. So make sure you change your front to negative z. So now, as you can see, while we don't have any extra functionality, we can use this camera class to replace that view and projection matrix that we originally had. So now with this, what we can do is we can simply go into this camera class and add some abilities to move around. So let's first get moving around working, and then let's get looking around, which is the harder part for sure. So for this, let's go into our input controller method here, and let's get some inputs in. So this is by far the easiest part. If you've ever worked with Unity, pretty much like that. So all you do is you can just say like if input dot is key down, and then it's keys dot, and I like to do WASD, but you can do whatever you want. This is Minecraft, so that's what I do. And let me just go ahead and copy this 4 times, and then WASD, and then now you are definitely tempted to simply do like position dot, or for W you would do position dot z minus equals 1 or something like that, but this is not correct. The problem is that when you rotate your camera, z does not change. So you are defining z as going forward and backwards, but when you rotate your camera, you are no longer going in z. And so let me show you a little example of this, what I'm actually meaning here. By default, we are looking in this position. So if we press, for example, D, we will go to the right following the X. But let's say we rotate, and now we turn right a little bit, and now we're facing this way. If we press D, if we're just adding to the X, we're still going to move along that X axis. And so we're just going to move at our incorrect angle. And this can get extreme when, for example, we look all the way over here. Then even when we press D, we're still going to be moving in this direction here. So we can't just outright change the position like this unless you are making a game where the camera cannot be moved or rotated, I mean. So with this being said, let's get into how to actually make this work. So what we're going to do is we're going to do position plus equals front multiplied by the speed variable multiplied by a float typecast of e.time. And this is so we can use delta time, and we'll get into more about why we use this later. But basically it's just for making it so that if we're running at really low frame rates or really high frame rates, that it doesn't change how fast we are doing things. And so for A, it's a little bit different. So what we do is we do position, and then we do minus equals, and then we do right times speed times, and then we typecast float e.time. And then for S, we simply do this same thing we do for W, but in the negative position, in the negative direction, or subtracting here. And then for D, it's just the same thing as A, but adding instead of subtracting. And so now this should work. So now all we have to do is in our now we have to simply update these vectors here or actually we don't have to do that yet, but we have to call this update here. And so what we're going to do is we're going to go into our on update frame, and then all we have to do is call camera.update. And you'll notice that this update method the camera update method takes more arguments than the on update frame has. So let's just add them here. And we don't add them in the arguments here. We do we simply just define them here. So I'm going to do mouse state mouse, and then we're going to do equals mouse state, and then we need to do keyboard state input equals keyboard state. And so now we have our mouse state and our keyboard state. And so here we're going to just simply pass these in. So remember that we take the input first, the keyboard input, the mouse input, and then we need these frame event args. So now we're just calling the camera update method. Remember, this camera update method is calling our input controller. So every frame we are checking for these inputs and performing these operations whenever they are pressed. So now, if all goes well, if we press these buttons, as you can see, we can move all around. So now we have some super basic controls working here. So now with that, let's add 2 more simple controls before we get into rotations, and that's going to be going up and going down. And so for this, we are not going to be using this technique, because the thing about up and down is they never change in Minecraft, meaning that no matter where you're looking, if you press space, you are always going to be going up in the Y direction. And if you press shift, you're always going to be going down in the Y position. You're never going to be changing the direction that you're descending or ascending depending on your angle. So this is very simple. All we have to do is if input.isKeyDown keys.space, then we simply do position.y, and then we add the speed multiplied by the typecasted float e.time. And then for shift, you probably guessed it, you just subtract and make sure that you set it to shift. I think it's L shift, left shift. All right, and now if we run it, we can move around and we can ascend and descend. So now we have the pretty basic controls. Let's get into rotations. And this is where I do highly recommend looking into these links that I have below that will explain the actual math behind this. I don't have the time nor the actual qualifications to be teaching linear algebra, but I can basically show you how to implement it. So we're going to be using what's known as Euler's angles, I believe is what it's called. And this is we're going to be using pitch and yaw. And pitch is going to be controlling, like whenever we look up and down, that's pitch, and whenever we look side to side, that's yaw. And so we're going to be using these. So I'm going to make a new comment in our fields here, and I'm going to make this called view rotations, I guess. And then I'm just going to make a private float pitch. This is going to be just declared, and then we need a private float yaw, which is going to equal negative 90 degrees. So the reason that we're setting yaw to the negative 90 degrees is to make sure that we are pointing it in the negative Z direction by default. So with this, we can now add a couple more things. We want a private bool first move. We're going to set this equal to, and then we want a public or private. It depends. I'm going to use public vec to last position. I believe we will use it in other classes, so might as well make it public. And now with this, let's go ahead and go into our input controller here, and we're going to do a couple things. So we're going to check if first move, and this is going to do last position equals a new vector 2. And here we are going to be taking that mouse argument that we sent. We're going to be getting the X position of that and the Y position of that. And then we're going to be setting the first move equal to false. And that's all we're going to be doing. And the if first move is true. And then otherwise, we will calculate the offset of the mouse position. And what we're going to do that is we're going to make we're going to make a var for the delta X. This is going to be equal to the current mouse position, which is mouse X, minus the last position dot X. And then we need the delta Y, which is going to be equal to the mouse position dot Y minus the last position dot Y. And then after we do this, we simply assign the last position to the new current position. So this way it's always just one step behind, pretty much. So this will equal a new vector 2, and this will be mouse.x and mouse.y. All right, and now we need to adjust our yaw and our pitch. So let's go ahead and do that. So the way we do that is we just do yaw plus equals, and then we're going to do delta x multiplied by the sensitivity variable that we created, multiplied by the float e.time. And then we need the pitch, which is just pitch, and we're going to minus equals the delta y multiplied by the sensitivity multiplied by the float e.time. So this handles some rotations. We have to do one more thing. We have to actually call our method called update vectors. And here we're going to be updating all of our vectors. So let's go ahead and get into that. So here in our update vectors method, we're going to do a couple things. So we need to basically calculate where the front is now, because we use the front a lot in our calculations. So we need to be able to calculate it. And so what we're going to do is we're going to do front.x equals mathf.cosine. And then what we need to do is we need to do math helper dot degrees to radians, and this is going to take in our pitch, and then we need to multiply this by the mathf dot cosine of the math helper dot degrees to radians of the yaw, and then we need to do front dot y is equal to the mathf dot sine of the math helper dot degrees to radians pitch, and then we need to do front dot z is equal to the math f dot cosine of the math helper dot degrees to radians of pitch, and then we need to multiply this again by the but it said actually this time we're going to do math f dot sine of the math helper dot degrees to radians of the yaw. And that is a lot of stuff. Now all we have to do after this is we just need to normalize it. This is just a mess. Otherwise it would be really weird. So we're going to do vec3 dot normalize and then just send in that front argument. And now that we updated our front, we need to update where our right and our up are. So all we have to do is we have to use, we have to just say right equals vec3 dot normalize. But instead of sending the right, we're going to do vec3 dot cross, and this is going to take in the front and the vec3 dot unit y, and this basically just cross multiplies these two variables here and gives you the output as the new right. And now we need to do the same thing with the up, which is vec3 dot normalize, vec3 dot cross, and we need to do it with right and the front, and that gives us our up, because if we cross multiply the right with the front, we get the up. If you want to just memorize this, I don't blame you, because that's totally kind of what I did. As soon as you get it, and as soon as you start to understand a little bit more about linear algebra stuff, it should make more and more sense as you go along. So now with all of this done, and we have the call here, in theory, this should work. And we're looking around, and boom, we can look around. Awesome. So we have regular 3D camera, but you'll notice that my mouse is all over the place, and it gets kind of hard to look around now because my mouse is in a weird spot. Let's go ahead and change that. So the way we change that is we simply, at the very bottom where I create the camera, I'm just going to do cursor state equals cursor state dot grabbed, and this should just simply hide our mouse and keep it within the frame. So there you go, we have that regular stuff set up there. And then one more thing, I'm actually going to rerun this again. What you might notice is that if you look down too far, you will actually invert your view, and I think if I keep going here, yeah, there you go. I can just go all the way around, which is not very good. You don't really want to be able to do that because it can be kind of weird. So basically, it's a very high level right here. You solve this with two if statements in your update vectors. So whenever you update your vectors, I would just go up here at the top and just say if pitch is greater than 89 degrees, because that's like almost at the extreme of the top, then pitch equals 89 degrees. And then in the same way, if pitch is less than negative 89 degrees, which is the bottom, then pitch equals negative 89 degrees. And now when we run it, you'll notice that we can look down, but it doesn't go on forever. We have a maximum. And one more note, now that we are using a proper aspect ratio, we can change this screen resolution to be something that you actually want, because I don't think you want to make a game that's 500 by 500. So I'm gonna make mine 1280 by 720. And as you can see, it is not distorted. It is still the cube that we had. And so that's pretty cool. And yeah, we can move into the cube. We can see all the stuff rotating and not get a seizure, hopefully. That's how that works. We now have a working 3D camera. I do apologize for not going super in depth with the rotations. I hope that you still managed to follow along. If you do want a more into tutorial, I'll have to brush up on my linear algebra. Other than that, I hope you found this tutorial helpful. In the next tutorial, I'm going to be showing you how to create your proper block class and draw multiple blocks. But with that being said, thank you for watching. Have a good day. See ya.